today we're going to expand on where we were started yesterday. Yes, ma'am. I'll just restate this. When there was no acceleration, the monkey lets go and stays there, and the bullet will travel along this same path it's traveling along because there's nothing to accelerate it. When we bring gravity back into it, both the bullet and the monkey are accelerated in the same way. So both have to experience the same change in velocity because they're both experiencing the same acceleration. And if you continue that further, they both would have to have the same displacement because they're experiencing the same acceleration, and although they have different initial velocities, their velocities are aligned because we aimed appropriately for the monkey. Therefore, the displacement below the path has to be the same as the distance that the monkey falls. Is that clearer? So what I would like you guys to do today is we're going to continue what we talked about yesterday. We were talking about rolling the car right off the table. I believe the bell got us yesterday. Is that right? Yes. So let's pick up right where we were, or at least as close to it as we can get. The desk was 0.86 meters above the ground, and we rolled the ball at 0.5 meter per second. Then you're asked to figure out where along the ground the projectile landed. With just a couple brief reminders. When the projectile reaches the edge of the table and leaves the table, its horizontal velocity still doesn't change. So the velocity when it makes it right here to the ground still has a component that is 0.5 meters per second horizontally. The acceleration is straight down. So although it will acquire some amount of y velocity, the horizontal velocity stays the same. To figure out where it lands, I suggested that we use a chart to kind of keep track of our information. And we got this far yesterday, right? All right. Okay. Oops. I don't mind rewriting this stuff. So I think that we all agreed that we're going to make upwards positive and to the right positive. Does that still work for all of you? So when we start going through this, delta y, 0.86 meters. It falls downwards. 0.86 meters, so I'm going to say that's negative. The crux of this one is that the initial y velocity is 0 because it's just traveling horizontally across the table. The moment it leaves the table, it still has 0 horizontal velocity. Don't know the final velocity, but it's being accelerated by gravity. We're looking for this horizontal displacement, otherwise known as the range. And in this case, we've been given how fast it's traveling sideways. There's a lot of data here, a lot of things to keep track of, which is why I think this chart is a good way to get yourself organized. We're going to add to this chart as our problems become a little more complicated, but there's clearly 3 pieces of information here. So you can use a motion equation to figure out that the time was 0.42 seconds. And that's where we probably left off yesterday. You need to understand that 0.42 seconds also applies to the horizontal motion of the object. So it fell for 0.42 seconds and traveled horizontally for 0.42 seconds. This is where some students in first period were a little confused, but there's no acceleration. So your range is going to be the product of the velocity and the time. Now, this doesn't come from nowhere. I mean, you probably learned this like in physical science, but let's say you didn't have physical science. It's the result of any one of these motion equations if you put 0 in for the acceleration. You just get this. So I think when you work this out, you got about what? It looks like it's going to be 0.2, like 20 centimeters, somewhere around there. or 0.2 meters. Now, this doesn't have to be the way the problem is stated. I mean, there's other things here. Like, here, let's see if we can't change it a little bit and see if you can roll with a new situation. What if I tell you that I have a table I don't know? But when I roll something off the table at 0.5 meter per second, it lands 0.6 meters away from the edge of the table. So I know where it lands, but I don't know how tall the table was. Can you roll with that change? See if you can. Give it a try. I'll pause it. Takes a moment or two to kind of digest where to begin. So I want to remind you of a couple things. Start here. It's very likely to be one of the best places to start if you're needing, a way to organize yourself. And for your next test, remember, partial credit is going to be based on you being able to interpret the problem. Then the best way is to organize yourself in some manner that's clear. Everything about the up and down portion of this problem is right here. So this is going to detail anything that's vertical, anything that's moving up or down or deals with up and down. Anything that's left to right, well, that's going to be over here. So when we're looking at the information that's here, anytime there's an arrow or something indicating going left and right, you're going to be putting it in the horizontal side. Anything that's going to be up and down, that's going to be in the vertical side. So there's only two numbers that are given, and they both look like they're sideways things. Now, just like before, you can kind of get an idea of where things have to go just based on the units in which they were given. Right? These have to be the units that are associated with those values. So when I'm looking across what I have here, it looks clear to me that I have a velocity, and it's pointed sideways, so that's got to be over here. I've got a displacement, and it's pointed sideways, so it's got to be over here. It's the only place it can go. Now, that's two pieces right there. It only takes two pieces to figure out the time on the right side. So I think we could get the time without even looking at the vertical side. But one of the problems is understanding what's being asked of you anyways. Before we even start the solution to the problem, I want this. I want the y displacement because that's a measure of how high the table was. So the only way I'm going to get that is if I have three other pieces of information on the vertical side. Now I know that it was gravity that brought the ball downwards. And in the case of this problem, it was similar to the other one, which suggests that it had no vertical velocity when it left the table. But that's all I know. In these problems, though, our goal generally is to find the time on one of the sides and use it on the other. So it looks like I'm going to need to get the time here first, and then plug it in over here to get the displacement second. Now, I would be remiss if I didn't at least stop and remind you that all of these values with the bar on them are vectors. It's a lot, but that should be enough to remind you to take at least a moment and make a decision about what's going to be called positive and what's going to be called negative. So if I am consistent from my last problem, I'm going to have to make that acceleration negative. Now I think I have a pathway here. I'm going to use delta x equals Vx times t. That should be able to get me the time. I have 0.6 meters equals 0.5 meters per second times t. Any question about where I came up with that? This is a good time to ask. All right. So 1.2 seconds, I think. Now that means it's 1.2 seconds here, but it's also 1.2 seconds there. The ball traveled sideways for 1.2 seconds and vertically for 1.2 seconds. So I've got 3 pieces on this side. That's enough. I cross that sucker out, and it looks like I can say delta y is equal to 1/2 a t squared plus v initial y times t. And you're going to use this for projectile problems. It's almost always that one. Now here's where I saw a few mistakes. 1/2 times negative 10 times 1.2 squared plus 0. When you work this out, you get a negative answer. But your answer is actually not negative. You get a negative answer, which is delta y equals negative 7.2 meters. It's negative because the thing fell downwards. The object's displacement was negative. But the table isn't negative 7.2 meters tall. It's just 7.2 meters tall, which is an impossibly tall table, by the way. I mean, that's top of the building here, so probably more likely rolled off a building. Seems to me that another practice is probably in order, based on what I observed in the classroom. So let's try another one. I'm sticking with this theme. I'm not changing the level of difficulty yet. We will have to change the level of difficulty soon enough, but we'll stick with this so far. In a movie production, a stunt driver needs to drive off the top of a building. And let's say the building is 20 meters tall. They need to strike a target that is 15 meters from the edge of the building. So how fast does the stunt driver have to be moving? All right, so similar question to before, slight variation, not much. But let's make sure everybody understands that. Start here and get organized. So vertical, horizontal, delta x, Vx and t, delta y, V initial y, V final y, a, and t. I know a lot here. So staying organized, I think, is important. But everything here fits only one way. It's like a jigsaw puzzle. So I'll stop talking.